So going over some exponential, I just spelled wrong at the top of the page, exponential functions that are EOC level style questions, some that are released and some that I just realized in the past that I've seen we're having some struggles with. That's what we're going to work on today. So the function f of x, 2 times 3 raised to the x, that exponential function, that means it is tripling and our a value is 2. So we started with 2 of something and then it is going to triple. And it was replaced with f of x plus k. So k, if we remember from yesterday's translations or transformations, is basically we're saying that this function, because that's f of x, plus k. And in yesterday's video and some of the previous work, we realized that k is going to be up and down translation. If there was an h value here, that would be left and right translation. So just sliding up and down or left and right. Now, the easiest way, in my opinion, to do this, which is the skill that we should know, is make our own table of our parent function. So where we started. So we're going to take f of x, we're going to plug in x and get an output for f of x. And that's your function notation. So I'm going to plug in an x value. I'm going to start with 0 because I like that one the best. And that's also going to give me my y-intercept of my new. And if it slides up and down, we could track it just along that y-intercept and have a great answer there without having to do too much more math. If you want, you could check one more point or something of that nature. This is a growth factor, so probably I will check a 1 otherwise because it's going up from here. And we're hoping we're going to get a 6 when we put a 0. And once we get our first one, we'll figure out where our first one went, and it will move towards 6. I'm sorry, we shouldn't get a 6 from the first one. So we plug in a 0, so 2 times 3 raised to the 0 power. Now, remembering our exponential laws, anything to the power of none, or 0, is 1. So we're going to distribute that 0 to that 3, which means this is going to become 2 times 1, which is 2. So our parent function, or the starting function, same idea, 2 times 3 to the x power at 0 would be at 2 here. If we do one more, let's say we'll do 1, and then if I plug in 1, so 2 to the third power, plug in 1 for the place of x, 3 to the 1 power, so anything to the 1 power is the exact same thing that it was. So 2 times 3 is going to be 6. So at 1, it would be 6 otherwise. So at that rate, I'm going to look for my good points on the one that is graphed, which is here and here. And you could argue these are good points, but this looks like a horizontal asymptote. And an asymptote is where that line's never going to cross. It's going to look like it's going to get really close, but it actually never touches that positive 4 y value. It's going to get really, really silly close, like 5.9, like 9, but it never is going to actually cross that 4. So then I want to track how I went from that 2 to 6, and that means I went 1, 2, 3, 4 up, and then we want to make sure it happened again. So 1, 2, 3, 4 up. And this question says plus k, so I know I'm tracking just the up. So the answer would be plus 4 because it went 4 up. And I guess it could have been down too, but in this case, from where we started, being our parent function here with that 2 to the 3 to the x, that whole function, so from here to here, slid up 4 units. So I've got a couple of these so you can figure them out. All right, so again, same parent function, the 2, 3, which we already did our table, which x and f of x. So when I had 0, it was 2. When I had 1, it was 6. So that means I started at 2, and then 1 was at 6. So my y-intercept is here now. My other good point is here. So instead of going up, it looks like my original line, which would have been here, decided to go 1, 2, so negative 2. So 2 down. 1, 2 again, so negative 2 down. So then the whole function slid down 2, so my k value is going to be a negative 2 because the whole function slid down 2. Now with a different function, so f of x equals 2 of x, which is really basic. That means we started with 1 and everything is going to double. So it was replaced with f of x plus k again. So we're still tracking an up and down slide, resulting in the function graphed here. What is the value of k? So I have a dot at negative 3 and a dot at 2. But I'm going to take my parent function again, plug in my x values, and get my outputs. It is growth, and I like starting with 0. So 2 to the 0 power. Remember, anything to the power of none is 1. So this is going to be 1. And then also, hopefully you know that because there's nothing here, and that should be your starting point with that 1 there. Like whereas before it was a 2 in front of the 2 to the 3 to the x. Hopefully you're picking up that that's your starting, your y-intercept as well. And then if I did 2 to the 1 power equals, so if I have 1 for x, and that's going to give me 2. So then my parent function, or the function that had the translation occur, was at 0, 1, and then 1, 2. Oh, and I skipped another good point. Whoops. 1, 2. In this case, we could actually, like, because there's another really good one at 2. Let's type in that 2. And we're doing this by hand because this is a calculator inactive question. So 2 times 2 is going to be 4. So at 2, it's going to be at 4. So this was the original function, and it made a change into the one that is now graphed. So we're going to check how many slashes. 1, 2, 3, 4. 1, 2, 3, 4. Yep. 1, 2, 3, 4. So our k value is a -4. So the whole graph slid down 4. Hopefully that made some easy sense. But the biggest thing is making those tables and comparing. So starting before it added the k value. So just with what was given. Now this is another EOC release question. So we have 2 tables. Which statement best describes her results? So the table 1 from temperature, method 2 temperature. The temperature using both methods changed at a constant rate. So the word constant rate means linear. So constant rate is a perfect, I'm just scratching it out. So we know as soon as you see constant rate, you think linear. That means, is it a linear function? Which means it's going to be addition or subtraction for our rate of change all the way down the side of our table. Then exponentially is obviously going to be multiplication or division, depending, but it's going to be changing by incremental, like super fast. It's not going to be a constant rate. And then method 2 is constant. And again, constant rate means linear. So that constant rate of change. And then exponentially, again, is by multiplication and division. So looking at our table, our x values are going up by 1, so that's perfect. So from 0 to 5, you could say we multiplied. You can't really multiply 0 by anything to get anything. So that's going to be complicated. So maybe it's an add 5. Well, that's an add 6. And that's an add 4. Add 4. Add 6. So not looking good for linear. So method 1 is definitely not linear because it's not the same rate of change. So 5 over 1, 6 over 1, 4 over 1, 4 over 1, 6 over 1 is not going to be the same. So definitely not linear. Again, there's nothing I can multiply by, but you can check this by doing 11 divided by 5. And then 5 divided by 0, which you know you can't divide by 0. So that's your big no-no. But 11 divided by 5 should match 15 divided by 11. So you're taking the one from the bottom, so working backwards. So 11 divided by 5 is 2.2. And 15 divided by 11 is 1.36. So that is not a constant by multiplication or division either. So method 1 is basically out for either one of these. So both is not going to work because method 1 is not linear, nor is it exponential. You could also put this in your calculator or in Desmos and graph it, like put the table in and see your dots. I cannot reiterate enough how important it is to put these things in Desmos and check these and make sure, because you can, and Desmos does all the math. You just have to know what an exponential function looks like and what a linear function looks like. So remember, exponential, if it's growth, is going to look like that. If it's decay, it's going to look like a form of this. Positive line, negative line, and obviously if you're a constant line or vertical line. But so if I could put that table in using the plus up in the upper left-hand corner in Desmos and see those plotted points, then I would also know that. So looking at method 2, 1.5 to 3. So again, let's take 3 and divide it by 1.5 in our calculator. 3 divided by 1.5 is 2. 6 divided by 3 is also 2. 12 divided by 6 is also 2. So I'm working backwards. So 3 divided by 1.5, 6 divided by 3, 12 divided by 6, and we're getting a 2. And that means this rate of change is times 2 all the way down. So each one, so it's doubling. is the word that you would see if this was written in a word problem. So doubling. So in this case, our second method is indeed an exponential function. It is changing exponentially. Our 0, so our y-intercept is going to be 1.5. Our rate of change is 2, and then this would be our function. And that 1.5 is, again, because the x is 0, that is our starting point, or in this case, our a, or our initial value. Number 5. Whew, this is a good one for an EOC inactive question. This is coming for you, buddy. Making sure you can start those tables and fill those in. So what is the largest integer value of x? So how big can x get such that f of x, which is the first one, is less than or equal to g of x? So you are going to make two tables, would be my suggestion. If you had a calculator, you would graph it and look for their intersecting point, because it does say that it could be equal. So they will touch at some point. And then after that point, f of x is going to be greater than g of x, we would assume, due to the style of question. But since it is calculator inactive, we are going to make a table. So we're going to take x, do our math, and then get out our f of x. So we'll do it for f of x first. So let's do, let's start with 0. So that's going to be 1/2 times 2 raised to the 0. And anything raised to the power of none is 1. So that's 1/2. Then maybe I'll do 1. So 1/2 2 to the 1 power, that's 2 times 1/2 is going to be 1. I'm going to start my table over here for the other guy as well and kind of stop to see, because linear might be easier for you to do and kind of pick up, because we're looking for when there's a great change. So I have that 5x plus 2. So if I plug in a 0, that's going to be 2, because 5 times 0 is 0 plus 2 is 2. If I plug in a 1, so 5 times 1 is 5 plus 2 is 7. 2, 5 times 2 is 10 plus 2 is 12. 3, so 5 times 3 plus 2 is 17, because 15 plus 2. We'll keep going. 4, 5. So 5 times 4 plus 2 is 22. 5 times 4 is 20. 5 times 5 plus 2 is 27. So we're adding 5. And you don't have to do the math at this point, because it's 2 plus 5, 7 plus 5. So 27. So at 6, if we extend it, then it's going to be 32. At 7, it's going to be 37. And at 8, it's going to be 42. 42. So add 5 more. 42. So I know this is going pretty darn slow exponentially. And we need to get where this is starting to outdo our linear function. So I'm going to go ahead and jump up to like 4. So if I put a 4 here, so 1/2, 2 to the 4th power. And remember, 2 to the 4th power means 2 times 2 times 2 times 2. So that's 4 times 2, which gives me 8, times 2, which gives me 16. 16 times 1/2 is 8. Again, not getting very big very fast, right? So let's go ahead and go with 6. 1/2, 2 to the 6th power. So if I went ahead and added another 2, so 16 times 2 is 32. And then one more, because 1, 2, 3, 4, 5, 6. And 32 times 2 is 64. We're going to plug that in and then half it. So 64 halved is going to be 32. So at 6, it's 32. And at this 6, it's also 32. Now, ideally, we should probably try 7. So if I add one more, that's 64 times 2, which is going to be 128. Yep. So add one more. So 64 times 2 one more time is 128. Half that is going to be 64. So that's 1/2, 2 to the 7th power. And again, you are not able to use a calculator on this question. So we're just doing the math, trial and error all the way down. You could also try to graph this guy on the on your paper, because you will have graph paper, but it's the same. You're still going to have to do the tables, whether you write it out as I'm writing it out or not, to be able to graph the points for the most part. So 7 is at 64. 7 is at 37, so that's too high, because f of x has to be less than or equal to g of x. So the x value that it asks for is going to be 6, because after that, it exceeds g of x. So then that means after 6, f of x is greater than g of x. So anything greater than 6 turns the function into the output being greater than the previous linear function. All right, so we are looking at our tables. We're going to write our exponential models from our tables. Again, we're going to pretend like we don't have a calculator. So -1 to 2, if we work backwards, so -2 divided by -1 is a +2. -4 divided by -2, so again, working backwards, is a +2. -8 divided by -4 is a +2. Hopefully you may have also already seen that this is times 2, times 2, times 2, and times 2. This is a 1-to-1, so we're great here. The only thing we are missing is our y-intercept. So remember, we're writing a b to the x power. So our b value is going to be 2 for sure, and our a value. So that means if this was 0, what would be here? So as I'm multiplying times 2 going down, working backwards, I'm halving, right? So half of 8 is 4, half of 4 is 2, half of 2 is 1, half of 1 is going to be a -1/2. So then it's going to be a -1/2, doubling to some amount. So y equals -1/2 2 raised to the x power. All right, so again, 10 divided by 4, 25 divided by 10, and then 62 divided by 25. Ideally, I didn't want us to do this with a calculator, but I'm not sure how we'll do it this guy otherwise. So we're cheating. Let's use a calculator. So 10 divided by 4, I get 0.23. 25 divided by 10 is 0.24 or 2.4, and 62.5 divided by 25 is 2.5. So it doesn't look like that it's actually even an exponential function. So this guy is not exponential. Maybe you could check it to see if it's linear, but it's not linear because that's a +6, that's a +15. So this is non-linear, nor is it exponential. Again, you could plug this in your calculator or in Desmos as a table and see that it's not going to be an exponential like the half pipe or have a consistent rate of change linearly either. So last but not least, we're going to see if this one is exponential and then write its function. So how did I get from 1 to 3? So you could either divide or multiply 1 divided by 3, 3 divided by 9, 9 divided by 27, 27 divided by 81. Or if you can see it coming down, you can see that this is divided by 3, divided by 3, divided by 3. Dividing by 3 is the same thing as multiplying by 1/3. So multiplying by 1/3. So that means we know in our a to the b to the x, our b value is going to be 1/3. We have to work backwards to get our y-intercept, and we are going to try to do this without our calculator. It's getting bigger, so if we work up, that's going to be 81 times 3, because 1 times 3, 3 times 3, 9 times 3, 27 times 3, and then so 81 times 3, so 3 times 1 is 3, and 3 times 8 is 243, so 24. So 243 is going to be our a value. And this is a decay function because you see the y values going down as the x values increase. So that's a decay function. So when you multiply by a fraction or divide as you're coming down or as you're going down the table or as the x values are increasing, that is going to be a decay function. All right, so Zach's wealthy uncle wants to donate money to Zach's school for new computers. He suggests 3 plans for his donations. He will continue the pattern in this table until day 12. So that means I'm going to go to 5, 6, 7, 8, 9, 10, 11, 12. He'll continue the pattern in this table until day 10. So 5, 6, 7, 8, 9, 10. And then this one, it says until 7. 5, 6, 7, 8, 9. Whoops, no need to go any further. Sorry, it was till 7. So I got excited. Too long. No need to track it that long. We just have to track it 3 more after our table. So from 1 to 4, what did I do? 4 to 16, 16 to 64. So the easiest way is to take, and you should and can use your calculator this time. So 64 divided by 16 gives me 4. 16 divided by 4, hopefully we know, is 4. 4 divided by 1 is 4. So that's perfect. And then so if I multiply by 4, so 64 times 4 is 256. 256 times 4 is 1,024. And then that number times 4 is 4,096. So for 7 days, if this was the way they chose, we would have $4,096 for him to donate. $4,096 for him to donate. This function, though, so our rate of change, so our A, B of X, so our B is going to be 4. And our starting amount, remember, this is as if we were going backwards, 0. So that's going to be 1 divided by 4, which is going to be 0.25. So it's going to start at 0.25. So he obviously gave 25 cents or input 25 cents for the it started with 25 cents in the account. Day 1, it became 1. Day 2, it became 4. Day 3, it became 16. Day 4, it became 64. All right, so just so all our numbers don't run together, and we'll change pin colors, but we're still doing the same thing. So for pattern number 2, how did I get from 27 to 9, 9 to 3, and 3 to 1? So 1 times 3 is 3, 3 times 9 is, or 3 times 3 is 9, 9 times 3 is 27. So it is going to be a multiple of 3. So my B value will be a 3. If I'm working backwards to my 0, it's going to be 1/3, which is 0.33, or you can just put 1/3 as our starting amount. So here I could do 1/3 times 3 to the 10th power because I want to know at 10 where it is, but we're trying to decide which one is the best deal across the board. So you want to keep going. So 27 times 3, because 1 might become a better deal faster. So 5, definitely our plan 3 is better than plan 2 so far. 81 times 3 is 243. 243 times 3, 729. Still a better plan so far. 729 times 3 again is 2,187. Times that by 3, it's going to be, and I'm going to bring it down, 6,561. And again, you could also put in 1 divided by 3 to the 3rd power raised to the 10th power, which should be the same thing as that. Yep, so 19,683. So 19,000. So already our second plan looks like it's better than our third plan. So second plan is better than our third plan because it's going to track for 10 days. And then looking at our first option, we are going from 1 to 2, which is times 2. 2 to 4 is times 2. 4 to 8 is times 2. Working backwards, it's going to be 1/2 because 1 divided by 2 is 1/2, which is 0.25. So 0.5 is 1/2. And then it's times 2 for an incremental however long for that amount of time. It's going to be our function for this one because it's doubling and it's starting would it be at 1/2. So if I double 8 to 8, I'm going to get 16, 32, 64. Oh, sorry. 128. 128 times 2 is 256. Times 2 is 512. Times 2 is 1,024. And then times 2 is going to be 2,048. So even though it was set for the longest amount of time, just doubling is not going to work. And then your plan 2 became a better plan because he was invested in it longer. If he had only invested in it for the equal amount of time, 64, 729, and 4,096, then this would be your better shot. But because the rate of time, the amount of time changed, big difference. So that tripling is huge in day 10. Huge, huge, huge. Way more than when it was doubling for 10 days. So expand the table and show that they're growing is what we've done. So the best plan for the most money is plan 2. All right, some word problem practice. So Kai's brother collects fuzzy insects called trivets. The trivet population decreases by 30%. So decreases by 30% means this is going to be a decay function. As soon as you see decay function, remember it's 1 minus our rate. Our rate is a decimal. So we have to change our percent to a decimal. To change a percent to a decimal, we are going to divide. So percent to decimal, divide by 100. Or move decimal 2 places to the left. So 2 places to the left. So I have my 30% here. That's important. So at 30%. So that means if I take 30% and to change it to a decimal, if I divide it by 100, that's going to move that decimal right there 2 places to the left. So 0.30 or 0.3. Make a table showing the number of tribits at the first 5 years for a starting population of 10,000. So at 0, we're starting at 10,000 because it's our starting population, which when we're writing our equation, that means it's our A value. So 10,000, 1 minus 0.30 for however long. And that's going to look like 0.70 to the x power. So if I did that by 1, so I'm going to decrease by 1. So 10,000 times 0.70, because anything raised to a 1 is itself. So 10,000 times 0.70 is going to be 7,000. And then 10,000 0.70 squared is 4,900. And then at that rate, then we're going to do our 3. So 10,000 to the third power is 3,430. Now, interesting to me is if I do 3,430 divided by 4,900, I get 0.7. 4,900 divided by 7,000, I get 0.7 as well. So something divided by this number is 0.7. So you could also have figured that out by knowing that 0.7 here. So it's a multiply by 0.7. So I could just take that 3,430 times 0.7, and that's going to give me 2,401. 2,401 times 0.7 gives me 1,680.7. And the way that we know this works is because, again, we started with that 10,000. It's going to be 0.70 as my decay. Or if none of that makes sense to you, all of this is fair game and is solid math. 0.30, you can put it in just as such and then raise it to the 5th power. It's 1,680.7. In what year will there be fewer than 1,000 tribits? So it's still 1,000 at 5. So maybe if I do 1680.7 times 0.7 again is going to be 1,100. So it's 6. The output is 1,176.49. So not quite there yet. 7. You could also go to your y equals in Desmos or in your TI-83 and put in that 10,000 to the 0.70, raise it to the x power, and then hit second graph and go get our table. And so we already know at 7, we're still, there we go, at 7 years, it's less than 1,000. So in what year will there first be fewer than 1,000 tribits? And that tribits because in year 7, there's 823.54 tribits. And I'm not exactly sure what a tribit is, but I'm going to bet that 0.54 is not good for conversation because that's going to be like half of a little like fuzzy bug, which is no good. So 823 by year 4. So year 5 is good. Year 6, we're still above 1,000. But year 7, year 7. I don't know why I put year 4. Year 7 is when we get, that is a 6 too. It's late, guys. Sorry. Year 7 is when we get to 823 tribits. All right. Maya's grandfather opened a savings account for her when she was born. He opened the account with $100, which is why we have 100 here at that 0, and did not add or take any money away after that. From the money in the account grows at a rate of 4% per year. So 4%, which we have to turn into a decimal. So we're going to divide by 100 or move that decimal 2 places to the left. Please make the loops because you will leave off zeros. So it's actually going to be 0.04. It is increasing. So it says grows. So that means we have 1 plus 0.04. And we started with $100 and it's going to be raised to the amount of time we track it. So at $100, something divided by 100 should give me 0.04. So that means 100 times 0.04 is going to give me 4. Oh, times 1.04. I'm sorry. This is going to be 1.04. It has to be greater than 1 for it to get bigger. So 100 times 1.04, 100 times 1.04, and it's 1.04 because that 1 is important for it to be a growth. And then 104 times 1.04, it's going to be 108.16. 108.16 times 1.04 is 112.49 if we round it to change because this is money. And then we also have that option of doing the 100 times 1.04 raised to the fourth power. So it gives us 116.99. So this money is moving pretty slow. 100 times 1.04 to the fifth power, 121.67. Again, this is an opportunity to go up here and do our 100, 1.04, raise to the x power. And you raise it to the x power because then I can go to my graph or to my table and I can see all the coordinates that work. So at 6, I have 126.53, and you can do the exact same thing in Desmos. 131.59, 136.86, 142.33, and then 148.02. So our rule is 100, 1.04 to the x power. And at 10 years, when she turns 10, that $100 has turned into 148.02. So it's not a huge substantial amount of money, but it did grow, like it said, at 4% per year. All right, just a couple more, guys. Hang in there. So a table shows that the elk population in a state forest is growing exponentially. So we know it's going to be a growth. So hopefully we know that's a 1 plus r as a decimal to the t or to the x. From the table, you can use your Desmos, and you can type in, remember, it's Y1 squiggle, which is in your keyboard, A times B to the X, and make sure you have a 1 after you put that table in. And that's over when you add the plus in the upper left-hand corner, you can put in the table. But if we don't have that, we can use our calculator here and know you can type in your table in there as well. So stat, edit, and put in our table, or just to discuss the parts. So 57 divided by 30 gives me 1.9. 108 divided by 57 is 1.89. 206 divided by 108 is 1.9. 391 divided by 206 is 1.89, which is basically 1.9. And 743 divided by 391 is 1.9. Now, that 89, we're going to imagine they probably round this up. It's population. So, and it went 1 every time. Ideally, you would want to use your good ones, but then we wouldn't have a 1-to-1 ratio on our x values. And if this is rounded in, it's still going to be 1.9. So super, super close. So our rate of change is 1.9. It is increasing because it says growth. So 1.9 is our rate of change. And our starting is at 30. Now, if you're unsure whether to put 1.9 or 2.9, because remember that 1 plus, what I would do is try it. So 3 times 1.9 raised to the 1 is 5.7. And that's not right, right? So 3 to the 2.9 to the 1 is 8.7. So something's still not right, right? So our starting amount, and it's because I have 3. Whoops, 30 to the 1.9 raised to the 1 power is 57. Boom. 30 to the 1.9 raised to the second power is 108, and then some extras. So that's because I didn't put my decimal again. Make sure you're using your calculator better than I am. 108.3, which is fine, right? It's super close because 0.3 is not a person. And we're talking about population here. So 30 to the 1.9 raised to the third power does give us that 205.7, and they rounded up to 206. So suppose the pattern continues, and these are elks, not people, sorry. How many elks will there be in 10 years? So that means this is a 1.9. So I'm going to do 30, 1.9 to the 10th power. Or again, put it in as 30 to the 1.9 It's a 90% growth. Whoops, 30 to 1.9, because that's 1 plus 0.90. So 1 plus 0.90. And remember, as a percentage, that's a 90% growth. They're doing a great job at growing there. Raise it to the x power, and we're going to end up getting our table. Go down to 10, and it's 18,393. So 18,393. So you can, again, go to Desmos and use the table there, and then write in your get the function, which is right here. And then from that, you could get your table to continue. Or once you do that, once you type in this in Desmos, go up to the gear in the upper right-hand corner of that section. It looks like a gear like this. When you click on it, it gives you the option to get a table, which we did when we were doing linear functions. So when you get the table for that, you could then type in 10, and then you could type in 15. Or again, you can put it in 31.9 raised to the 15, which is going to give us 455,434. So 455,434. How many years will it take the population to exceed 1 million? So we need it to go all the way up to more than this. So in my opinion, you can trial and error. So if this is 15, I would go ahead and jump to 20. And it does indeed look like 20. We are already there. So at 17, let's see what it actually gives me. If I type in 30.30 parentheses 1.9 raised to the 17, we're there. So we need to check and see if it already happened in the 16, and it didn't. So in 16 years, it was 865,324 and some change. So that's at 16. And then at 17, we broke into that million. So 1644116. And so that's where we get into that million spot. So after you're probably really between year 16 and 17, depending on when it made its change. So between year 16 and 17. So at 17, it will be above 1 million. Most accurately, you would say between 16 and 17. All right, last one. A city of 2,950,000 people has a 2.5 annual decrease in population. So that means we know it's 1 minus R to our time. Our starting amount was 2,950,000. And this 1 minus that 2.5%. We still need to change it to a decimal because there's a percent there. So we're still going to move that decimal 2 times or divide by 100. So 0.025 to our t. So 1 minus 0.025 is going to be 0.975. Raised to our t. So for 1 year, we're going to multiply this straight through. So 2,950, 123. Times 0.975, and you can raise the 1 if you want to, but remember, anything raised to the 1 is itself. So at 1 year, it's 2,876,250. So 2,876,250. So not a ton of people gone. Then we're going to do the same thing for 5. Or again, if you go to y equals, or type this number in this equation into your Desmos and start getting a table from that. So that's where we had our 2, 9, 5, 4 zeros, open 0.975. Sorry, I want to make sure I wasn't messing that up, to the x power second graph. So these e's to the 6 means that decimal is going to move to the right 6 times. So you may not like the way this looks in your calculator if you should choose to do it this way. But the idea is that e to the 5 is 2.6 e6. So just so you know what this is, 2.6 e6 means that that decimal is going to move 1, 2, 3, 4, 5, 6. So that means it's 2, 6, 1, 2, 3, 4, 5. So it's 2,600,000 1,000 people in 5 years. Again, so that E, if it's a positive number, means the decimal moves that many times to the right. If it's a negative number, that means it moves that many times to the left. Just so you're aware. You shouldn't run into it tons, but you might. So we want to know. So 0.975, and I'm missing a 0. Ooh. Raise it to the 15. So we have 20,17861.022. It's population, so let's get rid of that 0.022. And that's 2,017,861. Then we're going to do it one more time. And then you're going to tell me 25 years what our amount is. And that's going to be 1566525.282. Those points go away because point people is just arms and hands and body parts, and that's weird. So we're going to have 1,566,525 people at the end of 25 years. All right, guys, that's all things exponential. Hopefully that gives you some help and some things to look forward to as far as your EOC style questions and know what the expectation is of this unit. All right, great job, guys.